All right, so for our first question, right, question 5.27, right from the reading, they tell us we've got 0.25 grams of an organic compound. We burn it in this bomb calorimeter, and the calorimeter goes from 24 degrees Celsius to 26.43 degrees Celsius. They tell us that the heat capacity of the calorimeter is 4.13 kilojoules per degree Celsius, right? How much heat in kilojoules is the reaction, right? So for this, even though they gave us a mass of the organic compound, right, naphthalene, we don't need that mass. So it doesn't really matter that there's 0.25 grams of naphthalene, because this problem is just simply Q equals C delta T for the calorimeter, right? Because we have the heat capacity of the calorimeter and we know the temperature change of the calorimeter. I went from 24 to 26 degrees. So Q for the calorimeter, right, is 4.13 kilojoules per degree Celsius. And our delta T is final minus initial, so 26.4 minus 24, right? It's just 2.43 degrees Celsius. We know we can't use Q equals MC delta T because, yeah, we're given a mass of naphthalene, but we don't know the specific heat of naphthalene. We don't know any temperature change of naphthalene. So we can just use Q equals C delta T. So multiply those together, right? 4.13 times 2.43, and I get something like 10.0359 kilojoules, right? That's for the calorimeter. So what does that make our heat of the reaction? What does that make Q for the reaction need to be? Yeah, Quina? Yeah, because the calorimeter absorbed 10 kilojoules of energy, right? The reaction lost 10 kilojoules of energy. So let's see significant figures, right? Our delta T has got 3 sig figs. We got 3 significant figures there. So I would go to 3 significant figures and say negative 10.0 kilojoules or negative 1.00 e to the 1 kilojoules for question 27. You might think, 2 significant figures from the grams of naphthalene, but we didn't use that in our calculation. So it doesn't matter that there were 2, sig figs there in that number because it didn't show up in our calculation anywhere. Yeah, Sophie?
Do you recommend finding the heat of the, I don't know how to say it, or the reaction? Like, because there's a thing that's like heat of the reaction and it's negative C cal.
We basically did that right here, right? Without an equation, by just saying, because yeah, I gave you, and there's an equation, right? I gave you that Q of the calorimeter equals negative Q of the reaction. And then there's a version of this equation where it's, they basically say, oh, okay, Q of the reaction is negative C delta T. But we're kind of doing that same process right here by saying the reaction absorbs 10 kilojoules of energy, or the calorimeter absorbs 10 kilojoules of energy, which means the reaction released that 10 kilojoules of energy. The energy needs to be opposite in that case. Yeah.
Is it fair to say that when you use Q equals negative C delta T, that it's for the heat of the bomb calorimeter only?
That would,
you use the other equation for the rest?
That would be for the reaction if it was negative C delta T.
Okay.
And that's why I said, like, we're kind of doing that just in this step here of just flipping the sign for us. Yeah. All right, because we're in the reading, let's just stay in the reading for a little bit. So I'm not jumping back